Hello and welcome to today's webinar. My name is David Cash. I'm a member of the marketing team here at Mounts, and I'm glad that you've taken the time to join us today as we look at our topic of how friction impacts torque and the fastening process. Now, anytime we are doing a fastening, our end goal is that we are actually creating clamp force. And that clamp force is generated by the tension that we put on the fastener, which we use torque to create that tension. Now, the actual process of torque is related to the amount of frictional forces that it sees during the actual tightening process. So friction and torque kind of go hand in hand, and we typically look at friction as a coefficient of friction. And what that means by definition is going to be the tangential force that is needed to start or maintain uniform relative motion between two conducting surfaces, perpendicular forces holding them in contact. And in most cases, it takes a little bit more force to get things moving. But once they are moving, then we have a coefficient or a constant movement of friction. And so this little graphic can kind of help demonstrate that. So we have our cube here where we have a force pushing down on it. We can call that gravity. And if we try and push this cube, we need a certain amount of force to do that. Once we have applied that force and overcome the threshold of movement, then we move into our constant coefficient of friction. And so to look at this graphically, if we have our applied force versus our frictional resistance, again, as we apply load, we get to that threshold of motion, and then we kind of drop down into a constant state of friction. And so that's what is meant by the coefficient of friction. Now, when we see this represented in an equation, it is graphically represented by the Greek letter mu. And so in our formulation for torque, this is what this would look like in the coefficient of friction, which would be torque is going to equal our clamp force multiplied by the coefficient of friction. Now this is quite a lot going on within this equation. We have our torque, we have our clamp force, which are pretty straightforward, but then we deal with all of these components that within the coefficient of friction as it relates to torque. We're going to have to consider the pitch of the thread, the coefficient friction of the threads, the coefficient of friction on the bearing surfaces, the basic pitch diameter of the threads, the clearance of the diameter of the washer, the outer diameter of the bearing surface. So all of these components go into the coefficient of friction as it relates to torque. Now, this being a little bit confusing, we do have a way that the fastener manufacturers have come up with what would be a constant or a theoretical value for their fasteners as it relates to torque, and that would be considered a K-nut factor. Now, again, this is a constant that is being used for the coefficient of friction, and it's kind of a general purpose value that is referred to as a theoretical number, meaning that you can start here with this value, but your results may vary as it relates to your particular application. But it does make the use of trying to figure out what the correct torque might be for an application by using the nut factor instead of trying to calculate the entire coefficient of friction. And so this makes our formula a little bit easier. We have our torque is going to be equal to the K-nut factor multiplied by the diameter multiplied by the force. So this is a little bit more easier to deal with as it relates to formulating the actual torque value. The other thing that fastener manufacturers will provide is going to be proof load. Now, the proof load is basically the amount of stress or usable strength that a certain range for a fastener is. And so it will give us a certain amount of PSI that we are going to be able to stretch that fastener without it being without it being permanently deformed. And so in this example here, you can see that we have not necessarily a threaded fastener, but this rod will represent that in what we're trying to convey. So as the fastener, or in this case, the rod gets stretched, if we were to relieve the tension, the rod would go back to its original shape. But there's going to be a point at which it becomes perfect or permanently deformed. And you can see that right about here. That deformation will never allow the rod, in this case, to come back to its original state. So we have passed its proof load and past the yield point for that. And if we continue to pull, you can see it'll continue to deform, and then finally it will go ahead and break. And so graphically what this looks like is we have our proof load that comes up to our yield point, and then we have our failure. And so everything from the yield point to our failure point is going to be the plastic region of that fastener, and everything underneath the yield point will be the elastic region, meaning that the fastener will return to its original shape if we remove the load. And so proof loads are typically 85 to 95% of the yield point. And typically when we're looking at torque specifications, as a guide to start, we're looking at about 75% of the proof load. So depending on where that is, we can develop our torque specification from that. Now, if you want to try to replicate this scenario in-house for your own need, you can do that with the use of a torque analyzer and a rotary sensor. This allows you to put the tool in between, the sensor in between your tool and your part, and you can actually measure the torque output there. So you can graph this out and you can see exactly when you reach failure. Now there's going to be two scenarios that are going to happen. One scenario is your fastener is going to fail and it will completely break. The other scenario would be that your application actually will will break, and the fastener will still be intact. However, in that scenario, you want to make sure that you're measuring the fastener before you do the test and then measure it afterwards. If the fastener is longer than it is when you first started, then you're seeing values that have been reached outside of the yield point and outside of the proof load for that particular fastener. And so from there, you can make adjustments on your torque to make sure that you're not exceeding those values and that you're in a good spot for your particular application. So if you are having issues with a particular joint and its characteristics, this is one way that you can do a test on it. You can also use a regular dial wrench or a dial screwdriver to do the same thing. You just won't graphically be able to see the rundown itself, but you can measure at which point the actual application fails and make your determination about what you want to do at that point. So let's go ahead and do an exercise where we want to try to establish a torque value based on the fact that we know what the amount of clamp load or clamp force that we want to achieve. And so in this case, we have a hex cap screw, a 1/2 inch, that is zinc plated, grade number 5. And we know we want to achieve about 9,000 pounds of force to be able to hold our components together. And so what that formula would look like would be, if we're using the K-nut factor, is we want to take 75% of the proof load, which is going to be 75 or 0.75 multiplied by 85,000 psi multiplied by the tensile stress area squared. And that's going to equal 9,045, which is what we need. Then we would multiply our K-nut factor to that value, and then multiplied by the diameter of the fastener. And so after we calculate all of that, that is going to put us at 950 inch-pounds. And if we divide that by 12, that's going to equal the torque of 79 foot-pounds for that particular fastener, creating that amount of force. Now, if we wanted to do this same calculation, but we change one thing, instead of using a K-nut factor of 0.21, which was a dry fastener, we're going to use a lubricated fastener for our K-nut factor for the same screw or the same bolt in this case. But the only thing is it comes pre-lubricated, so it has a K-nut factor of 0.12. So if we do the calculations at this point, we are looking at a torque value of 543 inch-pounds, and we divide that by 2, and we get 45 foot-pounds. So in this case, we're getting the same amount of force that we would on the dry fastener, but the only thing that we're changing is we're using a lubricated fastener, and it allows us to have a torque value at 45 foot-pounds instead of our 79 foot-pounds that we would be dealing with for the dry fastener. So that is how we would do it. The issue becomes with if somebody uses a lubricated fastener for the dry fastener, then we might run into some problems, because if we calculate that using the lubricated fastener, that is going to put us at a force value of nearly 16,000 pounds of force as compared to the 9,000 that we needed with the lubricated fastener and its torque value. So we would be increasing our clamp load by 75% of that particular application. And so this is where we can see issues with the fasteners getting into and past the proof load or the yield point for a particular application, all because one fastener is lubricated and the other fastener is not. So anytime there is a material change or any type of change in the application, it can really change the clamp force that we are dealing with for the output on that particular torque. So everything that we would use for the dry fastening, the torque was the same. We just used a different fastener. Now, this, excuse me, the distribution of the torque that we are looking at that's happening during the actual installation and assembly process has a breakdown of this. And so if we're looking at a coefficient of friction of 0.08, we are seeing 45% of the frictional forces come from the head bearing surface, 35% from the thread friction on there, and then there is about 20% that is going to the actual clamp force or the actual stretching of the fastener to create the overall clamp force that we're trying to achieve. Now, if we increase this coefficient of friction to 0.14, you can see that our head friction has increased to 49%, and our thread friction has increased to 39%, and only 12% is going towards our clamp force. So as we increase the coefficient of friction, we are in some cases reducing the clamp force, for that particular fastener. And so if we look at this a little bit differently with our actual scenario here, where we have a coefficient of friction at 0.14 and our breakdown of 49 and 39 and 12 for our different outcomes. If we were to decrease our head friction by just 10%, what kind of influence would that have? And you might say, well, how can I eliminate 10% of my head friction? Well, this can be done very, very easily. Let's say the operator grabs a different washer that might need to be used. That particular washer may have a different diameter to it. It may be a different size. It may have a different coating to it. Or the operator may not use the washer at all and forget to use that. And so in that case, it would reduce our head friction. In this case, we go down to 0.126, which would be a 6% reduction in our head friction distribution. Our thread friction would remain the same. However, our clamp load would increase by 6%, and again, causing us an issue where we may be putting that fastener past its yield point. And so that's going to be a 50% increase in our clamp load for our particular application. And so you can really see that any type of change to the process or to the material can cause a great deal of impact to the actual clamp force. Now, if we did this in reverse and we added an additional 10% because the characteristics of the head friction caused it to rise, then we would be reducing our clamp force again in that area of about 50%. And so when we see failures, oftentimes the tool may be seen as the culprit, but it could be operator influence. It also could be frictional forces that are causing us issues. And so some of the influencers that can cause a change in friction, we typically will see lubrication is going to be one of the highest and easiest things to see as an influencer of friction. Either it's going to allow us to increase our clamp load, or it will decrease our clamp load based on if we're going from a lubricated state to a dry state or a dry state to a lubricated state. The coatings on any bearing surfaces that may be happening. So if there is a material change in the part, that can influence the amount of friction that may be happening. Also, tightening speed can cause changes in the amount of friction that is introduced, whether you're using a hand tool and it moves to a power tool, and that power tool runs at a very high RPM. That can heat the component, can cause issues that way. And that leads us into the temperature. That can also play a part in the frictional forces as well as the material pairings. So if you've got some alloys that may not do very nice together, that can be an issue that can cause some frictional forces change. And then again, if we change the geometry or the size of a washer or a fastener, that can play a part in the frictional output as well as the hardness of a particular material, if that again is not what was used when the torque specification was originally spec'd. So these are some of the areas that we see where the frictional forces actually can cause a tremendous amount of change in the final clamp load, which is what we're trying to achieve. And so we've had a couple of different scenarios where we've seen this play out in real life. And the first one is we use this example quite a bit, but We had a customer who had purchased an electric torque screwdriver, and we got a call from them a few weeks after that the actual tool was breaking fasteners. And so we had the tool sent in, it was looked at and serviced, everything looked fine. The tool was sent back and it did the same thing. We got a report that it was breaking fasteners. After a little bit further investigation, we found out that it was only happening periodically. And after a little bit more investigation, we found out it was only happening from one operator where they were seeing this issue. And it was only happening at certain times of the day. And so finally, it was figured out that it only happened after the operator came back from her break. And so when doing some observation, we found that when the operator came back from her break, she was loading or lathering her hands up with some lotion and then went to go ahead and use the tool. Well, with the lotion on her fingers, when she would grab the fastener, that little bit of lotion was adding lubrication to the fastener. And that fastener, as the tool would run down, would break that fastener because the coefficient of friction had been reduced and it was causing the clamp force to be much greater in breaking that fastener. And so we realized that it was the introduction of lubrication to that particular fastener that was causing the part to fail, and it wasn't the tool. We had another scenario where the customer had called in and said, your tool is torquing out early. It's, we're having lifted fasteners in there, and there's something wrong with the tool. Again, we did a little bit of investigation, and in this case, we did some graphing rundowns of what is happening in the actual rundown, and we could see that in the rundown that there was a tremendous amount of prevailing torque that was happening during the rundown. And it turns out that the customer had made a vendor change in the fasteners that they were using. And this vendor didn't deburr the fasteners as well as the previous vendor. And so those burrs were changing the coefficient of friction, causing it to be higher, and then causing the tool to sense that and torque early before the actual fastener was seated. And so in this case, we had to increase the actual torque output to overcome that additional torque made by the threads as they were going into the part, making sure that we're getting the correct amount of clamp force in there. And so typically when we see issues where it may be considered tool related, it actually can be more of the human element that is an issue, or a material change that may happen. So that is kind of the overall thing to think about, is how the frictional forces are actually playing a part in the actual assembly. So again, if we introduce things that are going to decrease the actual coefficient of friction, we're going to see a much greater clamp force. And then again, if we increase the coefficient of friction, we're going to see a decrease in the amount of clamp force, depending on how much stretch we are getting from our fasteners. So with that, that's going to conclude our presentation for today, and we'll go ahead and move into any questions that we might have, and hopefully we can provide you with the correct answer. So with that, Chris, do we have any questions?
Hello, Dave. Yeah, one of the questions we had is, does like a nylon locking nut or patch impact torque application?
So that is definitely going to play a part in how much clamp load is going to be seen, because as that patch or that nylon ring starts its when it starts to reach the threads, it's then now adding additional prevailing torque to the actual application. And so that is something that should be considered when we are installing a nut with a nylock ring. And so we make sure we get the correct amount of clamp force with that. So by doing some testing and graphing, you can definitely see how much additional torque may be generated during that prevailing. And then you'd want to take steps in adding additional torque to that particular application.
All right, Dave. Another question we had is how can joint relaxation be detected in the torque application?
So a joint relaxation, again, you want to be able to do a graph of what you might see with that, and then you could follow that up with a movement type of test where you can either do a marking test where you mark your part and your fastener, break that away, and then bring it back and see where you're at with your actual torque value. Sometimes when we're dealing with soft joints and really gaskety type joints, you may do another pass on those to account for any relaxation that might be happening. But those are typical of how you can measure how much you get compression and then relaxation of that. And that could be done through the use of graphing, either with a torque analyzer or with a tool that allows you to be able to graph that to see exactly what or how much relaxation is happening.
All right, thanks, Dave. Another question we had is can you address the friction changes during torquing with a flathead screw versus a panhead screw?
Um, that um, in my experience, the difference you will see is only going to be the relation to the bearing surface itself. And so, if there are different diameter widths of the bearing surface, then you would see a difference in change. The amount of uh, actual surface area is really going to be the only change that you might see. How that fastener is turned may not necessarily be um, the issue, but the amount of surface area that you're dealing with.
All right. Another question we had, Dave, was what is the impact of a thread locker on friction and torque, and does it act as a lubricant, reducing the friction, or does it tend to add friction, or add to the friction?
So that's a great question. Typically, if you're using a thread locker, it will decrease the coefficient of friction if you're using it as a liquid. And if it's being used in a scenario where that wasn't the original specification. And so if the original specification calls for the thread locker, then that should be already taken account. But in the event that it wasn't and it's being added later, it would definitely be a good idea to try and measure that to make sure that you're not, again, adding additional clamp force by reducing the coefficient of friction.
All right, Dave. Another question we had is can you share the comparison of RPM selection based on the friction of the material?
So I don't have anything that where you can compare it, but it could be material based when you are dealing with different componentries. That would be the one of the considerations because of the heat that may be generated. It may affect one set of material versus another set of material that can cause that fluctuation in the actual coefficient of friction.
All right. Another question we had, Dave, is What is the impact of fine threads versus coarse threads when you're typically applying it to the same K factor based on the bolt diameter?
So again, that's going to depend on the actual prevailing torque. So that might change because if a finer thread is allowing you to have a lower coefficient of friction, that may give you more clamp force as opposed to a coarse thread, which is kind of what we um, not. It's kind of a little bit related to our case study, but you may see an increase in the coefficient of friction dealing with a coarse thread as opposed to a fine thread um, in that scenario. So there could be a definite change in the amount of clamp force from those two, with it all being the same except for the thread.
All right, Dave. Another question we had is, how do you determine the appropriate torque to be applied to a specific fastener?
So again, that is going to be very, very part specific. And you'd want to do some destructive tests if you are having issues with a particular joint that's failing. Now, if it's failing because the parts are vibrating loose, you may have a situation where you're not getting enough clamp force. And then if the fastener is breaking, then you're getting too much clamp force. So you want to do that destructive type of testing if possible to see exactly at what value your parts are failing. Then typically you can back that off from about 75% to give you a good starting point to kind of target from, and then make slight adjustments either up or down based off of additional testing. So that is a good way to start. It's very difficult for a guide to say this fastener is has this torque value to it when it can play a big part in a lot of what's happening in the joint characteristics. Again, if lubrication is there, what type of material is being used, and sizes and things like that all play a part in the actual fastening process.
All right, Dave. Another question we had is, for testing or calibrating a tool that's not a power tool, like a hand tool, is it a good idea to use a rundown adapter or not?
Typically, you don't need to do that when testing a hand tool because there's not as much inertia that's being generated by the actual tool when it shuts off, like a power tool would. So using a hand tool directly on a sensor is not going to be an issue.
All right, Dave. Another question is, how would a curved surface influence installation of a fastener?
So a curved surface, if we think about it, it's going to be compressing the during the actual rundown. So that's going to basically increase the coefficient of friction as that is being used. So again, if you are using those types of washers, you definitely want to do some testing to make sure that when those surfaces come in contact, that you're seeing a consistent prevailing type of torque during that, because if those are used in the wrong orientation, again, you're going to then be decreasing the coefficient of friction and you're creating more clamp load. So the the big takeaway there is you want to make sure that they're always being used in the correct orientation.
All right, Dave. I think that's all the time we have for questions for today. The rest of them we will be able to respond to via email.
All right. Thank you very much for joining us today. And I hope, again, that you learned some information that can help you with your fastening processes. Thanks very much. And we'll see you again next month. Thank you.